lecture 35. So, contrary to what I said last time, it won't be actually possible to start on abstraction today. So, I will complete whatever I had to do on type checking in the context of contexts, and type inferencing and type checking in that with contexts, something that we had not specified last time. We had just assumed somehow that information was available in some form, especially for example, especially for the language of for the while language. The implicit assumption is that just as in the runtime case, we assume that there was a notion of a state. We are never starting with an undefined state, and that the notion of state that we assumed there in the runtime system was that there was a variable to value mapping available for every variable. Okay. Similarly, in the case of type checking, our implicit assumption, and since there are no declarations in the while language as we have defined it, the implicit assumption is that there is a variable to type binding implicitly available at the start, and given that that is always there, and of course since there are no declarations, we were forced to assume that there is an infinite collection of variables, all of them had some value assigned to them in the runtime environment. And similarly, now we will assume in the case of the while that we have an infinite collection of variables and they all have some type associated with them, maybe one of the base types. Yeah. So, with those assumptions in mind, we actually gave these simple rules for type checking. And one reason for giving such type checking rules is that they are very elementary, and let us dispose of expressions and get on to contexts. Get on to contexts, so that we get to know how exactly type inferencing is done, how type inferencing and type checking are related. So here was let us quickly run through this. So, we assume somehow that a context or in type information is available for the basic elements in the language, namely variables, and if there are constants, then of constants too. And we had these basic type checking rules, so that if you can somehow infer that E1 is of type tau 1 then and E2 is of type tau 2, then for any binary operation E1 binary operation E2 is of type tau 3, where tau 1, tau 2 and tau 3 are listed through these tables, right. And as far as commands were concerned, commands do not have a type. However, commands are made up of expressions. So, we have to type check commands in a way which guarantees syntactically that a command is somehow well formed out of the right kinds of expressions. So, with commands, since they are just state transformers, we just assume a predicate called well formed, and we will the type checking rules for the assignment command are that you should assign to a command only a value expression of the same type. You should assign to a variable only a value expression of the same type, and that you recursively go through the commands based on the structure of the command, and you type check complex commands in terms of the type checking rules for the simpler commands. So, if any of these components does not type check, is not well formed for some reason, then the whole command is ill formed, right. The whole command does not type check. And so similarly for the rest of the complex commands, it's just one extra type checking rule we require is that you actually have Boolean conditions and not arbitrary expressions. Okay. So, now let us actually look at it in the context of a functional programming language. with declarations. I don't want to mix up, I don't want to make the problem too complex by also having an imperative command structure. Essentially, this is to illustrate the use of contexts where you do not have an infinite collection of variables, you have only finite collections of variables available at any instant, and there are declarations which specify the types, in which case how is type inferencing done, right. So, if you were to extend this language to include a language of commands, essentially the type checking or type inferencing for the declarations and command and expressions would produce would proceed in the same way. In addition, commands would have to be well formed by appropriate rules, right. So, we'll not worry about commands. So, we'll just look at a simple functional language which is usually, which is like ML if you like, follows a similar syntax. So, we have these declarations. You can have a declaration of this form. In ML it would be val x equals something. In ML also you do not always need to give the type tau, okay, but that is because ML is not a type checking system, it is more than a type checking system, it is a type inferencing system. So, if the type of E is clear, then what ML will do is it will automatically assign that type to this variable x. So, we will come to that distinction later. So, right now we will assume that declarations are all well typed. So, which means we are actually imposing Pascal like declaration discipline in the language for the present moment, yeah. And then you can of course compose declarations in the usual fashion, and just for variety I have added an extra form of an expression, an ML type expression, the if then else, which is an important form. From the if then else it is also easy to derive options where you have options on the structure, options on pattern matching and so on, but that need not deter us too much. So, let us look at this. So, we have this expression with a declaration in it, and what holds for this expression with a declaration in it also holds in case you extend this to commands, for commands with declarations in them, right. So, Pascal like declarations are very easily taken care of, and then you of course you have these literal constants, right. In the case of declarations, the moment you bring in declarations, you are bringing in bound variables or free variables. The notion of free variables becomes important, and we had this definition of free and defined variables, right. This is so in a the base case is something of this form. The only defined variable here is x, and every variable that is free in E is free in this entire declaration. And when you compose declarations, you get similar structurally defined sets of defined variables and free variables. It is important to realize that right. So, the question is whether x can occur in E in the first declaration. Yeah. Now, the way declarations work in ML is that the x that occurs in E is a different x previously declared in some outer scope from the x that is now being redeclared. Okay. That x is still free. So, it is still a free variable of this declaration. Okay. So, if you took all x's in E, let us assume you give them a different color, the free variable x in the free variable set it will be of that color, whereas in the defined variable set it will be of this color, right. I mean that is, so this natural static scoping rules apply, and so any occurrence of any free occurrence of x in this refers to an x declared in some outer scope, right, and it has it derives its type also, just as it derives its value from that outer scope, it also derives its type from that outer scope. where that declaration for x occurs, right. So, and d1 semicolon d2 similarly has all these defined variables. The free variables of d1 semicolon d2 are that, well, anything that is free in d1 is free in d1 semicolon d2, and whatever is declared in d1 could be used in d2. So, anything that is free in d2 except those that have been declared in d1, this union constitutes the free variables of this declaration. Similar things apply here for d1 and d2, right. And of course, there is the disjointness condition for d1 and d2. The same name cannot be declared in both d1 and d2. That disjointness condition is made clear in the rules of inference. Okay, and then in the case of the nested declarations, a nested declaration is really a declaration that really refers to the declaration d2, which might be very complex. So, you might require additional names to abstract out some of the sub expressions and give them new names. So, you have the declaration d1 to aid, essentially what is required is the declaration d2. So, the only the only defined variables in this declaration are those that are defined in d2, and the free variables in this are all those variables that are free in d1, and as usual the variables that are declared in d1 might be used excuse me, in the declaration d2. So, the free variables of d2 excepting those that have been declared in d1, this union actually constitutes the free variables of this declaration. So, for all other expressions that we have already seen before, the notion of free variables remains unchanged, and in the case of this let expression, we need to specify free variables and declare defined variables in declarations in order to enable a definition for the let construct essentially. So, all this machinery is precisely for this. So, the free variables in this are exactly the free variables in E. Of course, the free variables in E could include some variables that have been declared in D. So, remove those because they get bound. Union, the declaration D involves expressions which contain variables previously declared in a scope, in the scope in which this let construct occurs, or in some outer scope in which this let construct occurs. So, the free variables of D are also free in this expression, right. And here of course, it is very trivial, it is just the union of all the free variables that occur in each of these expressions, right. So, a type environment or a context. So, now we are going away from infinite collections of variables. Since we have declarations, we can restrict ourselves to actually the variables or the names or the identifiers that you actually have in your program. You do not need to assume an assignment of types or of values to the infinite collections of identifiers that you have. So, we have the notion of a type environment, or what is called, what we have called in the lambda calculus, a context, right. So, a type environment or a context over some finite collection V of variables, this would be now a finite collection, is just a variable to types binding. Yeah, this types this types is meant to denote whatever are the types generated through some context free grammar in the language of types. Yeah. So, assume the, so for all identifiers, by the way, when we say variables, they could be, I mean, they are not really value variables, they could be identifiers which denote functions, right, or higher order functions, but for the present we will just restrict ourselves to this whatever types means. Yeah. So, in the type environment, over a given set of variables is just the set of all possible contexts that you can define over this set of variables. No, at the present moment I am not considering type variables. Yeah. So, there are no type variables, there are only value variables, but we have a set of types generated by some context free grammar. Yeah. In fact, for most of the examples here, this word types will denote only the base types, because I do not want to go into polymorphic types. Type variables are really required when you are dealing with polymorphism, but we have already dealt with polymorphism and we are doing a backward integration into lower levels. So, let us restrict ourselves to this for the moment. Yeah. So, just as in the case of our environments, we require the notion of a temporary updation on this static environment. Oh, by the way, this static environment is another word that is used interchangeably with context and type environment. So, a temporary updation of the type environment. So, given that capital gamma and delta are both contexts over some specified sets of variables, this updation of gamma by delta is such that for every identifier x, the type of x is given by delta if x is a defined variable of delta. Okay, so, if x is somehow a defined variable of delta, what I have done is I have stealthily extended the notion of defined variables from syntax to the contexts. So, essentially if you think of a context as a collection of this form, and so on and so forth, maybe z of type int, arrow, int or some such thing. If you consider context to be a collection of this form, then the defined variables are x, y, z, etc. Right. So, I have actually done that without explicitly mentioning it. So, we have the concept of what are all the defined variables in a context, and so this updation is such that if x does not occur in the defined variables of delta, then the type of x is whatever is given by gamma. Right.
Please explain this once more. T tau delta, I couldn't understand.
Well, I mean, he wants me to explain this. Well, gamma is a context, delta is a context, and gamma updated with delta is a new context. Okay. And how is this new context defined? It is defined in terms of the contexts gamma and delta as follows. Take any for any identifier x in the collections of variables over which gamma and delta are defined, the type of x is what you are interested in a context, and this type is whatever is the type of x in delta if x occurs in delta, if x occurs as a defined variable in delta. If x does not occur as a defined variable in delta, then the type of x is whatever is the type of x in the context gamma. Okay, so, this takes into account redefinition of a variable, right, over right. So, let us so how do we process declarations for type checking? We have so we have these rules of inference which are very similar to the rules that we had for dynamic semantics in the presence of environments, runtime environments. So, we are considering a collection of variables v, and essentially this context gamma has this collection of variables V as defined variables, right. So, given this amount, with this assumption of the types of the variables given in gamma, if you can somehow infer that the expression E is of type tau, then this declaration of x, this is a declaration of x, is well typed, okay. And what it means is that this declaration creates a new little context, just like we had new little environments. This creates a new little context which consists of a type binding for x, and that type binding for x is tau. So, the type of x is tau, and it creates this new. So, this rule actually does not do any inferencing, it does only type checking. So, it creates this little environment only if E has somehow been inferred to be of type tau. Otherwise, I mean, otherwise this rule is not applicable, which means that your declaration does not type check. Okay, I mean, the same kind of default rules that we had for the dynamic environments also apply here. I mean, what is not specified is not allowed, right. So, so if E were of some other type, some type other than tau, then what it means is that this rule does not apply, because this declaration does not type check, and therefore no new little context is created, and essentially the translation stops right there, right. No further translation takes place. I mean, because remember that this is something that happens at translation time as opposed to our runtime environment. In the runtime environment, if none of the rules applies, then what you can say is that essentially the runtime environment, the execution stops there, aborts, it does not give you any result. Okay. Similarly, the translation stops here if something does not type check, right. Okay. So, now more complex declarations. So, now declarations produce little type environments. So, in the context gamma, okay, which means somehow all the free variables in D1 have type bindings in gamma. Assume that all the free variables in D1 have type bindings in gamma. Then, since each of those declarations in D1 may be something like this, for example, each of them they create a collection of bindings of. So, this processing, assume that we can somehow create a collection, a little type environment which creates the bindings for all the defined variables in D1. Then, since the defined variables of D1 could be free in D2, in this updated environment where delta 1 is the little environment created by processing D1, and of course, it might contain some new variables V1. So, in this updated type environment, if you can infer that D2 creates a little context delta 2, then in the original context gamma, this declaration D1 semicolon D2 actually creates the little environment delta 1 updated by delta 2. Note that this allows for the fact that the same variable might occur in both D1 and D2. Okay. This is not allowed in languages like Pascal, but it is certainly allowed in ML. Okay. And so what happens is that the updation takes. So, within this after at the in the context of this composite declaration, the most recent declaration of that identifier is what is what is used throughout, and this the same thing happens also in the runtime environment. Yeah, the value of the most recent declaration of the identifier is what takes effect. Right. So this is how contexts are created, and now for the other two declaration mechanisms we have this. So, of course, here we have this disjointness condition on the side, that the declared variables of d1 and d2 should be disjoint, okay. And given that they are going to be disjoint, both d1 and d2 are type evaluated in the same context gamma within which they occur, and if each of them produces a new type environment delta 1 and delta 2 respectively, then this composite declaration produces a new type environment delta 1 union delta 2, and this disjointness condition ensures that delta 1 and delta 2 are also disjoint, and so the same variable does not occur in both. Yeah. And finally, for the within construct, as I said, d1 is nested, I mean d1 is used in order to essentially create the environment d2 or the type environment defined by d2. So, so what you have to do is, and of course the defined variables of d1 might occur within d2 as free variables. So, which means assume that, so we first process d1 in the context gamma, and let us assume that that creates a little environment delta 1 with of course a new collection of variables v1. Now, in this updated type environment gamma delta 1, process d2 to obtain a new little environment type environment delta 2, and the net result of this declaration is to create this new type environment delta 2. Yeah. Right. So, now we have seen how actually declarations create contexts, and now the type checking becomes quite easy. So, we can look at type checking with contexts. So, right. So, if you have if you assume you are given a collection of you assume you are given a context gamma, which means a collection of variable to identifier to type bindings, then that is a context we will carry throughout. In the case of these integers and so on and so forth, assume that there is some syntactic mechanism by which even without explicitly specifying it, maybe you can infer the type. So, in which case, or in other cases you might actually require an explicit declaration of this form. So, in either case any constants somehow are their types are obtained by pattern matching of the forms. For any variable, of course, for any free variable, its type is really whatever is defined in the context. Yeah. And for let us say these Boolean variables, we have the same old rules, except that they are all in the presence of a context, right. So, we have these trivial type checking rules. E1 is of type tau 1, E2 is of type tau 2, then E1 circle E2 is of type tau 3, where again of course the tau 1, tau 2 and tau 3 are as defined by these tables here for integers and booleans, right. And so, so what it means is you carry forward these tables for type checking here. And lastly, the if then else is just, it should ensure that an ML type inferencing actually means that in the case of commands, as I said, well formedness is enough. There is no question of command having a type. But in the case of an if then else used in an expression language, the whole since a whole expression denotes a value, it denotes a value of a certain type. Okay, so a whole expression denotes a value, so that it denotes a value of a certain type, which means both arms of this conditional should have the same type. The result of this expression is going to be either the result of evaluating E1 or the result of evaluating E0, depending on whether E is true or false. So, essentially this whole expression is of some type tau, which means that its eventual value that it returns in execution will be a value of type tau, provided each of these arms E1 and E0 is of type tau, is of the same type tau, and of course, this has to be a Boolean, otherwise it is not a conditional at all, right. So, if this is a Boolean and each of the arms is of the same type, which is not necessarily ensured in if then else in a typeless language. In an untyped language, what can happen is that these E1 and E0 could be of different types, and you might, and the result of this if E then E1 else E0 may not be compile time determinable as a type. You could actually have different types, and at runtime after the evaluation of booleans, you will actually, when you get the value, you will also get its type. But in an ML type environment where we insist ML is strongly typed in the sense that at translation time the type of every expression is determined, then this expression must have a type, and it can have that type only if both E1 and E0 are of the same type, right. So, that is how the if then else works here, right. And as far as let expressions are concerned, we will just so you have a declaration which creates a new type, little type environment delta, then you evaluate the type of this expression in the context of this new type environment delta. So, you look at it in this updated context, determine the type of this expression, and then where of course, the side condition is that this delta might use new identifiers. So, this V prime is the set of all defined identifiers in the declaration D. Then that in the context gamma, the type of this let expression is really the type of this expression E, right. So, let so this is how so in a completely closed program you will start just as you started with an empty runtime environment, you will start with an empty type environment, and as you go through the declarations you will be building up contexts. As you get as you go into inner and inner scopes, your context will keep getting updated, okay. As you exit scopes, your context will also keep shrinking, just like the runtime environment keeps shrinking as you exit more and more calls, till at the end again you are left with an empty environment, right. And that is at runtime, this is at compile time, that is the only difference. That since it is at runtime it specifies values, this is at compile time it specifies only types. Yeah. So, there is an interest. So, this is an interesting analogy between the structure of typing and the structure of, for example, the runtime environment. There are other very interesting analogies too, but we will look at that maybe later. So, let us briefly look at typing. I initially said that typing is an important concept because it allows you to save on badly typed runtime executions. So, if you do type checking, you can throw out a program early in the game without even bothering to execute it, right. So, and as so and it has been noticed that typing is that even experienced programmers make type mistakes, and so it is a good idea to have type checking or type inferencing. So, the difference between type checking and type inferencing is really this, that actually they are both closely very related. So, if you look at languages like ML and CAML, what happens is that now you in any ML session or a CAML session, you might be declaring a large number of identifiers. I mean, one does not necessarily need to think of an ML program as a one complete whole. After all, the fact that you can go through an interactive session means that you can keep changing things, and so as a result, in a really long session you will be using a large number of identifiers, some of them useful, some of them useless as time goes on. But whatever may be the case, what ML or CAML requires is only that you specify just enough type information so that the ML typing system can deduce what is called the principal type. Forget about the word principal for the moment, it can deduce the type of the expression. That is why it is not necessary, for example, to for every new identifier to introduce a declaration like you do in Pascal, right. You can keep introducing new identifiers, and as long as the ML type system accepts them and assigns them a type, you are playing safe, right. So, it actually does a form of deduction, and this deduction is a form of equation solving using unification. So, we will look at a small example of that, but essentially it does deduction. So, it does type inferencing from very little type information. So, it means that you require to have very few explicit type specifications for identifiers, and the types of all other identifiers and expressions are inferred, especially since ML uses pattern matching. The use of pattern matching means firstly that it can use unification to do type inferencing. Secondly, it means that since pattern matching is also a facility in the language, it means that programmers are going to use a large number of identifiers, and they do not have to be explicitly, they do not all have to be explicitly declared, right. So, ML actually infers the types of every identifier, and then type checking the expressions is no problem. Okay. So, type checking and type inferencing actually go on at the same time. And further, for identifiers which do not have explicit base type definitions. So, for example, I can define this function, let us say head, for a list in ML as normally I would, so head of I am using incomplete pattern matching, okay, right. So, I will just define this pattern h const t, and I will say that this is equal to h, right. Now, the point about ML is that there are now at least there are 3 new identifiers. One is head, another is h, and another is t. The types of none of them have been explicitly specified, except that I use this reserved word fun, and therefore this it is clear that this head is not actually a base type, that is all it specifies. But this application says that this head is actually a unary function. Let us assume that there is some precedence. Okay. So, for example, if I put brackets, if I do not assume precedence and I put these brackets, then what, so all that you can really look at and infer from here is that head must be a unary function, okay, of well, from this cons you actually infer that, which applies on lists of some kind, I do not know lists of what kind, and and if you have this, if that list satisfies this pattern h cons t, then I return h, right. So, what ML does is it actually assigns a type variable. Since the types of h and t are not explicitly specified, all that ML, so ML says that this function is really a function from some alpha list where alpha is to the type alpha, where alpha is a type variable. Okay. And since ML is polymorphic, what it means is you can, for example, apply head to the list consisting of 1, 2 and 3. Okay. From the very syntax of this, ML gathers that this is of type int list, and it actually tries to apply head to this and sees whether it can do it, and it can apply head to this only if it can equalize this alpha list with int list. Again it uses its own pattern matching facility and infers that alpha therefore must be int here, and it assigns, for this particular context, it assigns head, it assigns alpha the value of int. I mean, this is like a trivial equation solving. When can what is the value of alpha such that alpha list equals int list? Well, the value of alpha is int, right. I mean, it's the most elementary form of equation solving. It does that and it gives you an int, and then it actually types check this. So, this is int. So, if alpha is int, then this type checks. So, you could, for example, apply this head again to something else like true comma false, and then it actually does this alpha list equals, so this it knows is a bool list, and then it does that equation solving, and for this application it does the type check, right. So, but ML actually is capable of very complicated type checking, type inferencing, equation solving with the unification. So, it uses all these as these words like list as function constructors in a unification algorithm. Arrow is also a function constructor in a unification algorithm. Okay, the base types are maybe int, bool, real, whatever. There is a type language, all other things are function constructors over which unification has to be performed. So, for example, you could have alpha arrow alpha list. I mean, you could have a list of functions, right. So arrow, list, even the record constructor, the tuple constructor, they are all the star, for example, for tuple constructor, for the tuple type constructor, they are all function symbols to be used in a unification algorithm. So, for example, list is a postfix, this pattern, this not this string, I should not call it this constructor is a postfix function constructor over the language of types. This arrow is an infix constructor over the language of types. The star is an infix constructor over the language of types, and it uses all this and does the unification algorithm, runs a unification algorithm to do equation solving, right. And having done the equation solving and having inferred the values of all these variables, not all variables will if I stop my ML session here, alpha will not have an explicit value, it is still a type variable. Okay. But the point is that it assigns a principal type, that means it finds the most general unifier of that set of equations, the most general unifier is usually not expressed in terms of a monotype always. If this is my ML session, okay, and I use head over undefined kinds of lists, let us say I use head over lists of functions of type alpha, arrow, alpha and so on and so forth, then that alpha is never actually given an explicit base type definition in the language of types, it remains always a type variable. Okay. So, it generates new type variables and does unification and finally has a list of type variables which might actually be in terms of which all other type variables are expressed. Yeah, and that is how it solves it. Now, but whether it is simply typed, in the case of if it is simply typed, if it is a simply typed language, then what it means is that at the end of a program, this at the end of something, this alpha should have an expression, I mean alpha should solve to an equation of the form int arrow int or something in terms of the base types. It should be an expression, it should be a type expression in terms of the base types. But if it is polymorphic, I just leave it as a variable and I do the type checking, assuming that all the type variables that I have got have somehow been expressed in terms of some minimal set of type variables and base types in the type language, right. So, if you look at, so let's quickly look at this example. Here's the example of sorted. Okay. Now, if you do not give this declaration, so there are lots of identifiers here, h, h1, h2, t, sorted, they are all, there is no declaration for any of them, but there is a declaration for this h1 and this declaration is required. For example, because you are going to use a less than or equal to relation, okay, and this less than or equal to relation is not defined over all types, it is not a polymorphic relation. It is a relation that is defined in the ML environment only for integers, reals, maybe characters. For example, it is not defined on strings. In your own environment, you might have defined something like a less than or equal to for some other data types, but then you are still being absolutely specific about it. So, this less than or equal to is not a relation that is freely available over all types, and therefore, the only way ML can type check this is if it knows which less than or equal to are you using. Then what this declaration actually explicitly specifies and determines the type of the entire thing. For example, from this declaration it follows that this has to be an int list and therefore h2 has to be an int, therefore t has to be an int list. Okay. Therefore, this empty list is the empty list of int lists and this h therefore must be an int list and this nil is also the empty int list. And then of course, then this less than or equal to type checks for integers, it does not type check for many other types, and this whole thing is a boolean. So, sorted is has a type which is int list to bool, right. So, all this, so the programmers are lazy and would like the convenience of not explicitly specifying types, but then when they do not explicitly specify type, they also make type mistakes. So, the best way to combine convenience with typing is to do type inferencing, which is what ML does. The other extreme of course is something like Pascal, which do only type checking. They expect that every identifier has an explicit type specified, and after that they only do type checking. They do not do any type inferencing. The type inferencing is restricted to expressions, but then that is for checking consistency, and that kind of type checking can be done trivially by just matching arities and so on. It does not really require a sophisticated type constructor collection of type constructors to do it. So, languages like Pascal do only type checking, and actually even though I have written no inferencing, they actually do some inferencing. After all, expressions come without predefined types. Every expression is not type defined by the programmer. They do that amount of type inferencing which is already given by the rules, and they do the type checking to essentially to maintain consistency of types, right. So, and so essentially that's how type checking goes on. So, type checking and type inferencing are, I mean, they go together. If every identifier has been explicitly declared, then you require to do only type checking, but you use the same set of inference rules for both. If not every identifier is declared, then you have to do type inferencing, and you might require sometimes in that example of sorted, if you do not explicitly specify somewhere that something is that it is an integer list, either in an implied form or in an explicit form, if you do not specify in some place by which the inferencing system can determine what is the type, then it automatically gives you a message, unresolved type or some such thing, or ambiguous type, okay, unable to resolve type. Yes, that's the message it gives. So both ML and Pascal are actually statically typed languages, in the sense that the types are determined at compile time. That is what static means. They are strong, actually Pascal is quite strong, but I have written weak here for a specific reason, and that is to do with variant records, where you can do type mismatches. Okay, but otherwise both ML and Pascal are strongly typed. Pascal has other weaknesses also, like for example in procedures which have functions as parameters, the types are not clearly determined, and they are not determinable really at compile time, except at the call, but more or less Pascal assumes, but more or less Pascal is strongly typed. Most types are determinable. APL and Snowball and so on do not actually have a notion of compilation. They are very highly interactive. So, they have a very weak dynamic type checking facility. Just before the operation is applied in the execution, they actually check the consistency of the types and see if the operation can be applied. Lisp and Scheme are mostly untyped, except for the underlying base types, for which type tags are already available in the hardware or through firmware or through assembly or some such thing. Right, so that is how typing goes. Right. So I will start on abstraction next time.